Welcome to the IFE event. A couple of quick notes and thank yous before we start up. First, I want to thank PricewaterhouseCoopers for hosting us this evening. The Pricewaterhouse is also corporate sponsors of ours, so we appreciate them hosting and giving us space tonight. Our press policy is that all IFE events are off the record. If there are any press members out there, you're welcome to come up to our panelists afterward and ask for specific permission, but our general policy is off the record. All IFE events are recorded. There'll be a recording here, so for IFE members, just keep in mind that the recording is only on the stage, so your voice will be picked up, but your face will not be seen on the recording. And with that, I will turn it over to Michelle Cruey, who will be moderating this evening. Thanks.
Good afternoon, everyone. Tonight, we're lucky we have a fantastic panel with two of the best experts in the modeling of training derivatives with Igor Alfred and Dan Rosen. My name is Michel Cruey, and I'm a member of the Credit Committee of IAFE. And tonight, I play the role of the moderator. I just prepared a few slides to introduce the topic and positions both presentations in the landscape of the new frameworks to model structured credit products. I need some help to... David? Okay, we all know that the standard model for pricing and CDO tranches is the single factor Gaussian copula model, where you can use alternative copulas. These models are easy to implement for prices in terms of one parameter, the base correlation. In some ways, it's very much like black and shorts, where you, for equity derivative, where you price options in terms of implied volatility. Or except that when I say it's easy to calibrate, it's not true. I mean, in the recent period, we came up with very steep base correlation curve, especially for the CDX, with correlations of 100% for the, even more than 100% for the super senior tranche. So there's obviously something wrong with this framework. So copula models have many shortcomings besides the one I just mentioned. They are unable to reproduce implied correlations for quoted tranches in a simple way. They are static models, so they are only good for single period instruments such as CDO tranches, whose prices depend only on the marginal distributions for given dates. There is no dynamics for credit spreads, and therefore you cannot use these models to price more exotic structures, such as forward starting tranches, options on tranches, or leverage super senior tranches. And also, even you don't need a dynamic model of the evolution of the spreads to price a CDO tranche. The deltas with respect to CDS computed with under copula models are inconsistent, since they don't contain the spread risk. So there is obviously a need for better models, more sophisticated dynamic models. We have many dynamic models that have been proposed in the literature. But as I say here, very few have actually reached the implementation stage. You have the multi-name default variable models in the spirit of Black and Cox, which use the representation of default time as the first exit from a barrier of a state process. The problem with this approach is you end up with very complex formulas, even for discount factors. And it's pretty computationally intensive to derive the CDO spread. Next, a family of random intensity models in the spirit of Duffy and Galliano. They introduce randomness in spreads by introducing random default intensities. And the challenge is to choose a random intensity process to obtain closed form solutions for CDS spreads as affine processes. The problem also with this approach, the pricing of multi-name products is done through Monte Carlo simulation, and it's very computationally intensive. We still don't have the computing power today to implement this kind of approach into production. Last, we have the models based on portfolio losses, which is the topic of today, and two somewhat competing approaches, the bottom-up approach that will be illustrated by Dan Rosen for the pricing of bespoke CDOs. Here, the idea is to calibrate implied default probabilities to credit default swap term structures. You need to model for dependence through either a copula or a factor structure model, as Dan will propose to obtain a joint distribution of default times, and then use numerical procedure to compute the risk neutral distribution of portfolio losses. The top-down approach, the alternative framework, here the idea is to view the portfolio credit derivatives as an option on the total portfolio loss, and you build a pricing model based on the risk-neutral market-implied dynamics of the aggregate loss. And here you have two families of models, if you wish. The approach proposed by Sean Busher, which models directly the term structure of traditional distribution of the total portfolio loss. The problem with this approach, it's still at this juncture, it's still a framework, and specification needs to be done. Then last, you have the approach proposed by Igor Alperin in the spirit of Gesicki and Goldberg, where you model the spot loss process. And I let Igor to introduce his model. So while Igor is getting ready and joining on the podium, I will introduce briefly the speakers. Igor Alperin is with JP Morgan. Is responsible for model research in the area of portfolio credit derivatives. His interests include the calibration pricing method for bespoke portfolios, top-down and bottom dynamic model for multi-name exotic credit derivatives, as well as the modeling of credit portfolios with alternative underlying such as LCDS and CFDS. And Igor holds a PhD in theoretical high energy physics and worked in academia before moving to the financial industry. Dan Rosen is next speaker. Is a co-founder and president of the consulting firm R-Square Financial Technologies. He's also a research fellow at the Friel Institute in Toronto, and a professor of finance at the University of Toronto in the master's program in mathematical finance. And prior to that, Dan spent 10 years with algorithmics in various roles. Among them, he was the head of research and did some very interesting and clever work on in credit risk modeling and economic capital attribution. And Dan holds a PhD in chemical engineering from the University of Toronto. Igor.
Is going to be about modeling credit portfolios with a top-down approach, and what I'm going to cover.
Please speak into the mic.
Okay. So I'm going to cover following items. First, we'll talk a little bit about why we need multi-period models. Then we'll talk about different types of multi-period derivatives. We'll talk about differences between top-down and bottom-up approaches. Then we'll discuss two examples of particular top-down models. One is a model that was developed in-house called Bidaeus Spread Loss Portfolio Model, BSLP for short, and another model developed by Kai Nisike and co-workers. TCBP stands for Time Change Build Process. And the last, I'll talk a little bit about the current research in these models, namely how we get single name calibration and single name dynamics in those models. So when we talk about the need in multi-period models, we can differentiate between three potential areas of applications for those models. The first one is pricing of exotic products, which are products that include part dependency or and/or optionality. The second area of application is counterparty credit management, where we typically need to calculate counterparty credit exposure by simulating distribution of future mark-to-markets. And last but not least, as was mentioned by Michelle, we strongly believe that we need dynamic models in order to get consistent single name hedges. Now, I'll mostly talk about the first area of application called modeling multi-name derivatives. Because that's my main field, but also I'll mention the other two as well. So when we talk about multi-name credit derivatives for a newcomer, sometimes it's not easy to get oriented in this rich universe of different portfolio derivatives. But broadly speaking, we can differentiate between two major families of portfolio derivatives. The first class of instruments is so-called single name instruments, and the typical examples of instruments from this class are CDO tranches, CDO squared, and default baskets. The second class is formed by more exotic instruments such as forward tranches, tranche options, or leverage super senior. The basic difference between these two families of instruments is that to price the instruments from the first class, you typically only need to know the marginal loss distribution for a sequence of future times. While to price the second instruments from the second class, you need to know much more. You actually need to have some sort of dynamic model that models joint dynamics of spreads and losses in a portfolio. In other words, you need some volatility assumptions for the second class of instruments. Here is a typical example. Here, what is shown here is a typical trade. If we take a view of buyer of protection, so we buy protection in this example on a 5-year tranche, which is 4 to 5%, and the payoff, namely the payoff of this tranche, which is the tranche loss as a function of portfolio loss, is shown here. So it's the typical call spread option. Tranche losses are 0 when portfolio losses do not reach 4%, and then it grows linear, and then when portfolio loss reaches the level of 5%, then the trade dies. And on the bottom you see the cash flow diagram. So we pay 60 bips quarterly, and then we get in return we get payment on losses. Mathematically, things look like shown here. So first we define the first formula shown here is the expression, mathematical expression for the this tranche payoff. K lower bar and K upper bar are lower and upper strikes for the tranche. Now, to get the fair spread of a tranche, as you probably most of you know, we have to calculate values of both legs of the tranche. The default leg, which is the price of selling protection, and the premium leg, which is the price of buying protection. Both are functions, as you can see here, both are functions of expected tranche loss at different values of time. Right? Now, when we equate the two, we get the formula which is shown here, which is the formula for the fair spread of the tranche. The most important fact is that about this formula is that, as you can see, the only thing we need to know to price a tranche is the series of tranche expected losses for different values of future time, which enters both numerator and denominator, and nothing more. So we don't know. We don't need, for example, a dynamics, meaning the law of change of those expectations when you change small t, right? This would amount to some sort of dynamic model, but here for this example we don't need that. So, and this is quite similar to the way how you price a bond. If you have a bond, you only need to have to price it is just today's yield curve, right? You don't need to have any sort of dynamic assumptions about how yield curve evolves in time. Now we can make one step forward to consider a slide which seems to be a slight modification of this basic structure. Namely, we add an embedded option to this trade, an embedded option to cancel the tranche at 3 years. So this embedded option is essentially equivalent to buying an option to sell protection, meaning buy risk, for the same tranche, 4 to 5%, for the same spread of 60 bips. The option matures, so the option matures at 3 years, and then it covers the remaining lifetime of the tranche, up to 5 years. The cash flow is shown here. Now, obviously, this option will be exercised only if the future mark-to-market of the tranche is positive. And the way you calculate this mark-to-market, you again calculate the value of default leg, the value of the premium leg, and you subtract the second from the first one, and keeping the coupon fixed at 60 bips, and this gives you mark-to-market of the tranche. So then it means that the present value, the way we value this embedded option today, will be given by this expression, which is pretty standard. So it's just we take the positive part of the future mark-to-market of the tranche as given at 3 years from now, and we take an expectation value and discount it to present time. Right? But what is peculiar about this formula is that you can clearly see that what enters this valuation is the future distribution of losses, right? Because mark-to-market value at 3 years from now will be determined by how the market perceives losses between 3 years and 5 years. And this is illustrated in this graph schematically. So what you see at the bottom is a schematic picture of evolving market environment. So these red lines are some sort of combination of spread and loss dynamics. And for each point in time, you have different loss distribution. For each scenario, you have different forward loss distributions. Now, to summarize what I have said so far, the difference between single period models and single period products and multi-period products is very similar to the difference between bonds and callable bonds in interest rate world. To price the former, namely stake with forward products, you only need to know today's yield curve. But to price the callable bond, you need to know how this yield curve evolves in time. Same thing here. For CDO tranche, you only need to know today's view of future losses, but to price a tranche option, you need to know how it will evolve in time. Now, and obviously, this imposes some this problem of valuation of such payoffs, such as tranche option payoff, requires some consistency conditions on the joint dynamics of spread and losses, because it's quite obvious that, as I tried to show schematically on this graph, it's quite obvious that if you think, for example, about what sort of spread distributions spread distribution you would have at 3 years from now, then it's clear that this spread distribution will be severely constrained by loss distributions at 3 years and 5 years from now. So it's not very well defined, this consistency at this stage, but it becomes when we get down to modeling properly. Now, this is what about the first application of first motivation for those dynamic models. The second motivation, which I mentioned before, is the calculation of counterparty credit risk exposure. So mathematically, it's very similar to the previous problem of pricing the tranche option. Namely, if we have a risky counterparty and we do a trade, we trade a CDO tranche, then we stand to lose mark-to-market, the positive value of mark-to-market in the case of counterparty default. So again, we have the same problem of finding this expected our expected losses by calculating distribution of future mark-to-markets of the tranche given a particular market scenario. Again, a similar graph to the one that we showed before. And finally, I would like to mention the third potential application. Even though the common market practice is currently to take static models such as credit metrics, or Gaussian copula, otherwise known as Gaussian copula, to calculate single name hedges, it's very far from clear that this procedure is consistent, because by its very meaning, static models are only today's snapshot of future of our view of future losses, and it's not clear at all that we can consistently calculate single name hedge ratios in such a model that essentially doesn't take into account any spread dynamics, as Michelle mentioned. And indeed, I know of at least a couple of papers which are cited here at the bottom that address this issue and compare actually single name hedge ratios in models that include dynamics and also include contagion, that I'm going to discuss next, with hedge ratios calculated in Gaussian copula framework, and difference very often quite substantial. So this so far about the motivation, and now let me switch to presenting a modeling framework. So as we saw previously, if you get back to this formula for the price of the tranche option, or the previous formula for the fair spread of the tranche, what stands out in those formulas is that what you need to know to price those instruments are just expectations of total portfolio losses, or expectations of tranche losses, which are functional to portfolio losses. Then this idea was a motivation behind developing this class of top-down models. As long as the only thing we need to price those instruments is the total portfolio loss, let's just model it directly without first getting to the stage of typical stage of bottom-up approach, where we start with single names and then build things up. Then, if we concentrate on directly modeling portfolio loss process, then we can start with modeling a related quantity, which is just the default counting process. So n of t, let n of t be a default counter, then with the number of defaults that happens up to time t. Obviously, it should be increasing integer valued function. And then, depending on how we model recovery, the loss process, L of t, is related to the default counting process, either by simple scaling. If recovery is constant, then they are directly related, as shown in the last line here. If they are not, what you can say is that they jump at the same time, but the magnitude of the jump for the loss process will be random if the recovery is random. Now, the simplest idea of having a discrete integer valued increasing process is obviously a Poisson process. So if we assume that there are no simultaneous defaults in infinitesimally short time, then we can discretize this process. We can put it on the binomial tree. So we'll get this sort of tree. In each step, as you see here, in each step what happens is we either have in any node we either have defaults, then we move up, or we don't have a default. So those are probabilities. In each node, the default happens with probability lambda times dt, where lambda is the intensity for some process, and no default happens with complementary probability of 1 minus lambda dt. Now, to implement this is really simple, and it is really simple as well to convince yourself that this model has no chance to fit anything, because it only has one parameter. It has one parameter, and moreover, it doesn't model contagion. So the portfolio, if lambda is the portfolio intensity, then the portfolio intensity stays constant between defaults in this model. And this is believed not to be a welcome feature. So what we want instead is, first of all, to model contagion explicitly. Contagion in the sense that likelihood of defaults for surviving names should depend on how many defaults we had in the past. And also we would like to have more parameters to fit to tranche prices or possibly to exotic prices. So here I just show two examples of such more sophisticated models. The first one was suggested by Kadisik and co-workers. That's this time change curve process, where we say that the portfolio intensity is a linear function of the number of defaults that happen up to time t. So this is the first one not shown here. And then these C and G will be free parameters that we will try to fit to observable tranche flows. The second model is our in-house model called VSLP, that we developed at JP Morgan. It says that we model the portfolio loss process as a sort of nonlinear death process. So such that intensity of the next default will be proportional to the number of surviving names, which is the first factor here, and not minus n. It's just the number of surviving names that you have at time t, times some phenomenological factors, f of nt, which we call contagion factors. So the meaning of those factors is that they are responsible for default contagion and also indirectly for default correlations. If you set them to 1, then what you get will be what is known as linear death process. So imagine that f of n and t is 1, then the portfolio loss intensity will be decreasing function of the current number of current number of surviving names. Then it means that per name, the intensity per name would be obtained by division of this expression by this. So that means that when f is equal to 1, then per name you would have constant intensity equal to lambda naught. And you would have no contagion at the single name in the single name sense. Now, in this model, f of nt contagion factors are served as free parameters, and these are exactly parameters that allow us calibration to tranche pose. So we do it in a piecewise linear fashion. We assume that as a function of t, those factors are piecewise constant, so they're constant between 0 and 3 years, 3 and 5 years, etc. And this allows us term structure calibration. And in the loss dimension in n, those functions are piecewise linear function. And the number of nodes in this parameterization is always chosen to be exactly equal to the number of available tranche codes. So this model is a sort of semi-parametric model, if you wish, and in the sense that the number of free parameters is always the same as the number of your available tranche quotes, and therefore it can be easily used either for standard index tranches or for bespoke tranches as well. Now, so if we just stick to this model, it will be a model on its own. When we discretize, we get some sort of one-dimensional tree in the loss dimension, but this might be not exactly what we want, in the sense that we all know, of course, that empirically spreads change also in the absence of defaults, which means that if we stick to this model, then we would miss this feature. And another motivation to introduce something on top of this one-dimensional dynamics is our desire to have more degrees of freedom to feed, to adjust some exotic prices, such as prices of tranche options. Because essentially the previous specification, this specification has no free parameters. So parameters here are fit to tranche quotes. So the way we introduce this stochastic intensity in the model is very simple. We just multiply the previous intensity by a random factor. This y of t is a random process, and we choose it to be a non-negative process. For example, the one shown here is which is log normal mean reversion process, which can have diffusion term, and in addition, in theory, it can also have a jump term, which is driven by the same jumps in a loss dimension. So in this sense, once we do that, we have a two-dimensional model, which we call spread loss model, even though the first dimension is not exactly spread. This YT is kind of hidden process, but nevertheless it's related to observable portfolio spread. And the loss is also not a loss, but rather a default count. Anyway, we call it spread loss model. And it's when implemented, it's put on a tree, on a two-dimensional tree, in those tables, n of t and y of t. And because it's a tree implementation, it's very fast. And pricing of most instruments is done by backward recursion on this tree. For those instruments that have some path dependence, we have Monte Carlo implementation. Okay, so here there is an example of calibration, which is done on October 12, 2007. Typically, so that's a typical result of calibration. Usually, the quality of calibration is pretty good, and all theoretical marks obtained in this model are well within bit-ask spreads. I don't show them here, but that's the case. So this is what I have to say about the top part of this top-down model. Then there is a natural generalization of this model. Why those models are called top-down? Well, because we start from modeling the portfolio level dynamics, and then we go down to the level of single names. And this idea can be, in theory, can be implemented via the so-called random thinning procedure, which was proposed originally by Giesecke and Golder, and developed further by Giesecke and co-workers. So, first let me explain why we want this random thinning. For several things. One thing is the single name sensitivities. Once we calibrate the model to tranche quotes and then calibrate it to single names, then we can tweak certain parameters in this scheme and calculate single name sensitivities. Then we also potentially we can also apply this idea, this method, this methodology to pricing of bespoke portfolios. Having in mind the following: we start with calibration to tranches, to index tranches. Then once we dissect portfolio intensity into components corresponding to contribution of different names, we can combine them in a different order or take some subset of them and put them in a bespoke portfolio. That's how we get bespoke portfolio in this framework. And finally, we are interested in a sort of dynamic extension of this random finite methodology. The way it was proposed in Giesecke and Goldberg was essentially the static view. So it was the static view of how things look from today's time, the static view of future portfolio dynamics. If we get some sort of single name dynamics in a way which is consistent with the portfolio level dynamics, then we have a full-blown dynamic model, which is multi-name, multi-period dynamic model, and that can be applied in any situation where the more classical bottom-up models apply. Well, unfortunately, I have to skip this most interesting part of my presentation because of lack of time. I just want to show you maybe the last graph here, even though it's not very informative. So basically, what you can get in this picture is a sort of dynamic view how individual single name intensities change as a response to portfolio level defaults, and also as a response to some endogenously pulled volatility. So here is in the last slide, I show a couple of examples. What I do here is I artificially generate 3 defaults in the portfolio at 2, 4, and 6 years. And then I look at how my single name intensities, there are a few curves here because I model piecewise constant forward default intensities. So there is one set of intensities for the first period, 0 to 3 years, and then the second one for the next interval, 3 to 5 years, etc. So you see that all those curves get flattened after a certain time. That simply means that after 3 years, for example, the blue curve just switches to the green one, etc. So what is shown here is that actually you do have some sort of single name contagion in the sense that upon default, the single name intensity, especially for low spread names, jump up. Yeah, and the first graph shows how it happens when this externally put volatility is low. So essentially, you only update to default events, but if you, on top of that, if you put some sort of numerical noise, then these jumps become somewhat masked. So it's shown here in the low graph, and as this might be compared with the picture that we get for high spread names. For high spread names, what comes up as a result of this picture is that they are much more idiosyncratic. They respond less to portfolio events, and probably this makes some sense because they're already so much idiosyncratic that the spread is already so high. Thank you very much. Conclusion. So I tried to make the point that top-down models are quite flexible and useful for lots of different applications. The single name calibration is feasible, and I didn't show details, but the accuracy is not bad and can be improved further, and dynamic extensions are possible as well. Thank you very much.
Alternative views of dynamic modeling. And we'll take questions at the end of Dan Rosen's presentation.
So first of all, thank you all for being here in such a nice afternoon, and instead of being in the sun, coming and hearing some fun talks about pricing, CDO models, and things like that. So I really appreciate it. First of all, this is joint work with David Saunders of the University of Waterloo. There are some of the people who helped us done some of the implementation. And let me get going directly into this. So where are we today? And this is what I'd like to do. When people value synthetic CDOs, the Gaussian-Coppola framework is still the most prevalent. When people value bespoke portfolios, it's actually fairly difficult, and the methods that people use are fairly ad hoc. And as Igor spoke earlier, the application of dynamic models is still fairly new. There's this very new set of models which are starting to be applicable in practice and are starting to make their way into real applications. I want to also focus not only on synthetic CDOs. Synthetic CDOs is one of the biggest parts that has got attention in the market, but there's a lot less literature on how to price some more complex cash CDOs and other structured credit products. And in this case, valuation is more difficult, instruments are non-standard, it's more computationally intensive. In addition to default risk and spread risk, we have interest rate risk, and in particular there's prepayment risk or some form of cancelability risk in this instrument. Structures are a lot more complex, so it's very hard to go from the portfolio loss distribution to the tranche loss distribution or to the tranche cash flows, and that actually tends to require some form of simulation. And what people do mostly is one or two things. Either you simplify the waterfall cash flow structure so that you can apply some of the more sophisticated methods, or you simplify the model and treat them as simple bonds with a very fixed amortization structure. And that's the general idea of what it is. So one of my key points, and I'll try to give you some examples on this, is there's generally been a lack of an integrated view of these two types of instruments and how to price these things generally. And I'll try to hopefully get us a step further and to look at them in a simple way. So let me start with the very end. So it's those of you who don't stay till the end, at least you'll get the gist. Those of you who want to doze off after this, then I've told you everything I needed to tell you. I call it a scenario framework. Really the key idea is, and in particular, as we're going to go and model cash CDOs, we'll need to do some form of simulation. It's very hard otherwise to get the cash flows of these structures. So we want a framework where we have the ability to model the waterfall details and incorporate a full bottom-up approach. And I'll walk you through why that is important. So that's the first part. The second part is we find a nice way to think about these using factor models. And factor models for portfolio creditors have been used for a while, so that's the key idea and some of the key tools we'll have. We'll borrow some tools that have been used in options valuation coming from the weighted Monte Carlo literature. And we'll put together some of the CDO analytics that have also been mixed. So all we're doing is putting together actually a bunch of components and mixing them in a slightly different way. So basic idea is very simple. Imagine we can have a bunch of systematic scenarios. So some scenarios and some factors that are going to determine whether there's more defaults or less defaults in the economy, or more likelihood of defaults or less likelihood of these things. And based on some prices, we're going to try to get the risk-neutral distribution of that factor, of that economy-wide type of factor, and we're going to calibrate this to observed prices of anything that we have available to us, either CDSs, index tranches, or any other information which could be subjective, some prior distributions that we like, or some what I'll call quality preferences, some formal form of that distribution. So in one sense, one of its advantages, it's very flexible. One of its disadvantages, it's very flexible. And you can do a lot and you can do too much with it. So one of the things we'll do within this framework is just show you that modeling a cash CDO, that simply becomes modeling its a bespoke portfolio with a complex waterfall structure. So if we can model the waterfall structure and you can extract information from the bespokeness of the portfolio and use the observed prices, then we'll have something. Now, the methodology and the framework is very general. You can apply it in principle to dynamic models. Having said that, the examples we'll focus on are static in the sense that we can't really price with these examples and with these type of models where I'll draw the examples any options on CDO tranches or any forward starting tranches. The reason for that, and I'll show you, I think this is work in progress as we go along, is just parametrization and computing power to do it. So let me go very quickly. I'll start by introducing the problem by talking about pricing synthetic CDO. So we have a synthetic CDO. We talk about the key element that we need to model is the loss distribution of the M tranche at time tj. And for that, we need the loss distribution of the portfolio at time tj, and this is simply the notional times the loss given default for all the names, and we need an indicator function which tells us whether default has occurred before that time Tj, and the tranche, the function that converts from portfolio losses to tranche losses is a very simple spread option. As we go to cash flow CDOs, this function is going to be very complex and maybe not accessible in very simple analytical terms, but just from a simulation model. So let me try to walk you with pictures what we do in the Gaussian-Coppola model. In the Gaussian-Coppola model, we say there's a single factor driving the economy. Conditional on that factor, we have a set of functions. For each name k, we have the conditional probabilities that default will occur up by time tk, by time t for name k is given by that particular function. That's the function that gives you the Gaussian-Coppola, where phi is simply the cumulative normal distribution, phi minus 1 is the inverse normal, and fk is really calibrated to individual names. That is actually something that gives you the term structure in individual names. So in the end, rho k is that correlation function which gives you the correlation between the asset values, or in this case, the times to default for all the names. So conditional on each state of the world, we know the probabilities of default for any point in time for every one of those names, if we have those functions. And then we can calculate the conditional portfolio losses by just putting it there. And because conditional on that state of the world, things are independent, we have lots of tools to do that. Particularly the method mostly used, probably the recursion by Anderson et al. But there's other methods to do that. But the key thing is, conditional state of the world, we calculate the loss distribution of the portfolio for any point in time. But we're doing it bottom up at this stage. Okay? Then we translate this through this tranche function or instrument function to translate to tranche losses. We can get the expectation on each of those tranche losses on conditional state of the world. And we also can do that at every one of those states of the world. And then we can calculate the present value of buying protection, of selling protection, depends on that expectation, as Igor explained earlier. So does the spread, and all we need is those expectations over those scenarios. How do we calibrate the model? Where normally we calibrate that function fk of t to the spreads of each individual name. And for tranches, because, I mean, if the Gaussian-Coppola model was great, a single correlation number in their row would get you the value. But what we do is we actually find that doesn't work. So we find a correlation value for each tranche n. That's how we calibrate the model. But let me try to give you an idea of why this is. Okay, so the problem with that, it's great. We get we really don't do it for tranche correlation. We do it for base correlation, so progressive equity tranches. For those of you who know that, you already understood it. For those of you who don't worry about it. It's not important for the rest of my talk, really. But the key point is, I need a different correlation for different tranches. So how do I apply this to other portfolios? How do I apply it? So it's really a little bit inconsistent. It kind of looks and sounds or smells like Black-Scholes and implied volatility, but it's not quite. But let me try to give you a bit of intuition. We have a lot of other stuff that we could have calibrated instead of rho. For example, we could have changed the function phi. Instead of using a Gaussian-Coppola, people have used t-coppolas or mixture of normals or other coppolas. So the function phi with some parameters can be changed and calibrated. That's an alternative. We could also calibrate to the distribution of the factor z. So these scenarios have particular probabilities, but we're leaving them untouched. But there's no reason why we couldn't actually calibrate or change those. So we could change all of these things simultaneously, right? So there's many options for us to do, and every model takes a different option to do that. When you map these, so you obtain these base correlations for index prices. How do you apply them to bespoke prices? Well, that's ad hoc. What you do is you get a base correlation, which is the blue one, for your index portfolio, and you say, can I find what are the equivalent correlations for my bespoke portfolio? How do I do that? Well, I'll assume that this correlation here really corresponds to a level of risk. And level of risk is something very vague, and actually there's many different ways of defining that risk function f that I do there. But essentially what you do is you find within your bespoke portfolio a set of attachment points that will give you the same risk, and therefore you assume and basically you pray to how many gods you want that is actually the right mapping. But there's nothing fundamental about this mapping. It's just a nice intuition of this is what I think it is. and it's mathematically consistent, and it has a lot of problems. Actually, most of the time when I've used it and when I've talked to practitioners, you always find problems, and you always end up adjusting it manually and doing some ad hoc adjustment. The question is, there's some information in the market, I mean, the correlations of the market that come from this curve. That curve is a real curve. I mean, I might not want to express it as such, but prices in the market tell me something. How do I use that something to a different portfolio that makes more sense or is a little bit more systematic? That's what I'll try to grab about it. So let me go one step further. When we have cash CDOs, now the cash flow waterfall is a lot more complex. Now there's default, recoveries, prepayments. Collateral in these cash flow CDOs is very complex. They can come from mortgage security, they can come from loans. Those loans might have all kinds of different covenants in them. So you need a model to get the cash flows of the collateral, and then there's a cash flow model for the CDO, and if interest rates get paid, there's over collateralization. But in the end, you can get those cash flows with some very big set of rules, but it's not that easy as just putting a spread function. So we will need some form of ability to simulate to get to these prices. So that's a general idea. What do people do? So as I said, you either simplify this cash flow waterfall and then apply the previous set of models, or you make something very simple. You assume it's a bond, where the cash flows might depend on a set of factors, and these are matrix price, and you say, well, I'll use a set of prepayments and defaults and LGDs depending on the rating, and depending on the class, and depending maybe on the geography, and then I'll use a discount spread, which is also depending on the rating and maybe the asset class. But essentially, it's just a matrix pricing, a little bit sophisticated, but doesn't really capture very well what these instruments have. So we need something that allows us to do the same thing. So let me now go straight on to turn around the problem. So what do we do for bespoke portfolios, or what can we do? And here the idea is to say, instead of focusing on calibrating the correlation, and I'm going to oversimplify the problem, define that these scenarios there, and I'm using a one-factor model, but this is for a multi-factor setup. So we have a set of scenarios, that is a vector of factors. I'm from Canada, so I said Z as opposed to Z. And Q1, Q2, Q3 are the probabilities of these scenarios. So they might come from a prior distribution. They could be normally distributed, and therefore they come from there. We do exactly the same previous steps, and if we know that those set of parameters, Fj and rho, I can do everything as before. But then what we say is, if we know the prices of the tranches, instead of trying to change those rows, once we pick a function here, we try to calibrate by looking at changing the probabilities of those scenarios. What we're really implying is the risk-neutral distribution of a set of systematic factors. This is actually consistent with financial theory, right? I mean, in the end, prices in the market should only give us idea of premiums that are undiversifiable, that come from systematic factors. So this is a set of systematic factors. So we're trying to extract the premia in the market by looking at those prices. And so what we'll do is we'll say, give me those set of probabilities, and I'll try to change those weights, and sometimes I might have too many variables for too little unknowns, so I'll try to have a nice distribution. So I want to find these weights such that they match tranche prices, but it's also nice. Something I like, something I'm comfortable with to do. There's a mathematical formulation for that. So imagine this might be the prior distribution if it's a Gaussian copula and I use a Gaussian copula function, but as I calibrate, maybe the weights I get look like this. And that's what we will get, essentially, as we try to move through this problem. Mathematically, you write it like that. It's not that important. You maximize the smoothness function, which could be a maximum entropy, or a closest distribution to something you like, or could be a function that you like. Instead of getting a perfect match, you might want to have prices within bounds, or you might want to have a trade-off between matching all the prices and having a nicer distribution. And you might also restrict the weights to belong to a family of distributions. So you might say, give me the best normal inverse Gaussian distribution, or the best T distribution, assuming that that factor is distributed as a T distribution. It just makes it an optimization problem. You have to be careful. Really, the problem is solving this problem computationally in an efficient way. Sometimes very nonlinear. Sometimes, if you're not careful, you might get a non-convex optimization. But most of the time, it's a very well-behaved problem that is solvable. So that's the general idea. There's a lot of background literature on weighted Monte Carlo. I do want to make a point. The Holland-White's implied copula, which appeared a couple of years ago, is just like you can look at it as a one very specific, simple case of these models. I can, in the original paper, and those of you who are interested, the paper is posted in defaultist.com. We show that what that function is, and it's for homogeneous portfolio. It has some ad hoc extensions for bespoke portfolios, and what we've tried to do is just put it into a more general framework and a bit more consistent. There are a bunch of other papers who have some very similar non-parametric ideas. So let me summarize it. I use a single factor Gaussian copula type of function to do it. So we have a Pj of z is the cumulative probabilities of default for name j, conditional on the factor up to time t. If you use a Gaussian copula, that's a function in there. If you use base correlation, you change that. If you use actually the implied copula, you model that directly. Actually, you model it as a hazard rate, and you assume everything is homogeneous. What we're proposing is, let's go and model as a factor. Choose the proper functions, and those functions we can choose from a whole family of them. And there's first of all, we have real experience with credit portfolio models and calculating correlations between things for the last 10, 15 years. So there is some good empirical data to use. But in general, where we'll choose these functions is from this set of family that we call generalized linear mixed models. Just a linear function of the factors and some function of t. We need that to match term spreads for each of the names, the term structure spread. Now that's a static formulation. If we want the dynamic formulation, we just add an index t in there. Just the dimension just blows up by the number of time steps we take. So if we use, for example, a multi-factor copula, the function pj of z looks like a general distribution g, a general distribution h, which is an inverse, and some linear function. And in the paper we show if you use a Poisson mixture model, which is like a credit risk model, or a logic model, or a probit model, you can always choose what those functions look like. And now it's just a practical issue of how we do it, and how we choose this scenario. So let me go in the last 10 minutes of my presentation and give you examples. I think that's probably the easiest and the nicest way. Just a quick point. If anyone has doubt that systematic factors are what drive prices and what has happened, all we have to look is at home price appreciation, and this is the S&P Case-Shiller home price appreciation, which tells you the percent change of home prices on a yearly basis from one day to another, and you can see exactly how prices of underlying securities are correlated to these type of factors. So we have seen over the last year how this type of systematic factors exist and actually have physical meaning if you want them to have them. Let me walk you through some examples. I have 4 examples. I don't think I'll have time to do the 4 of them, so I go to 2 or 3. I'll give you an example of calibrating ADX, a CLO, and a high yield, and pricing against a high yield index. And depending on how much time, I'll show you a multi-factor model with concentration risk, or a 2-factor model where we have names in Europe and North America, for example. Let me walk you through the first example. So this is the ADX prices. I think this is around September, October last year. I forget the exact date, but again, those of you who are interested, there's a paper coming out with these second set of samples. So what's the ADX? The ADX references 20 asset-backed securities, asset-backed bonds, all of which their tranches are grouped into 5 different indices, which are rated between AAA and BBB minus at the time of inception. Trading began in January 26, but what's important is all of these indices, there's 5 indices, have the same underlying pool of loans. So there's no reason why I should price them using different parameters. They all refer to the same pool. The pool moves all those prices together. And I want to capture that as we price this. These are the observed market prices for the AAA is 91.81. For the BBB minus is $23 on par. So here's what we do. We discretize our world, and we're going to create, I think here there's 135 factor scenarios. There's a magic reason why it's 135. It's a Kabbalistic number. Actually, I don't remember exactly what we did 135, but there was a reason. But it's not important. And here's what I'm plotting. I'm plotting over all of these market scenarios. So think of each of these scenarios as a state of the world. And in that state of the world, the orange line gives you the average probability of default for each of the underlying loans in there. I think there's about 200,000 underlying mortgage loans once you account for all those 20 ABSs underlying the ABS. So that's the probability of default for each of these, the annualized probability of default. So it goes from the bottom, which is here, which is about 2%, to all the way to 30% a year. The yellow line, and I didn't talk about it much, is the prepayment rate. This is the annual prepayment rate. So in good states of the world, people default a lot, very little, but they prepay a lot. In bad states of the world, people default a lot, prepay a little. And the purple line is the loss given default. So again, in good states of the world, there's very small loss given default because property prices still retain their price, so you recover 90% of them. In very bad states of the world, you have Armageddon. So in these Armageddon scenarios, 30% of borrowers default a year, and every time they default, house prices and with everything, you actually recover only 20%. So they're like all these houses are taken by Mad Max, and there's really the scenarios. They follow these type of functions, and this is the correlation of the triangle. Under each of these scenarios, then I can get the cash flows for each of these ABSs, and I can present value under the risk-free rate. So what I'm plotting is the present value of each of those tranches under each of those scenarios. So assuming, say, the probability of that scenario is 1. So, for example, the purple line is the BBB minus, which actually goes on, once default starts to happen, it goes and loses its value, it goes almost to 0. And then the next one is the BBB, then the next one is the yellow line, which is the A, etc., and the orange line is the AAA. Right? So I'm revaluing, extracting the cash flows, present valuing under each of those scenarios. So then the next question is, if I could find a single scenario which prices each of those loans properly, or I can look for a set of weights and see what prices. So if I use a standard Gaussian copula type of model with average implied probability of 12% implied correlation, those would be the weights of the scenarios, and the prices would be all off. Instead of pricing the AAA 91, it will be priced at $3 above par. Instead of pricing at 23, the BBB, it will be priced at 48. So I can now go and find a set of weights that match those prices. For example, I can say, give me the best Gaussian copula or that would look like that. That would be it. It would have those parameters, and I would price pretty much everything but the super senior tranche. The only way I can price that super senior tranche is by creating a lot of weight here in those really bad states of the world. And that's the only way I can do it. I can go and say, give me the best distribution that matches these prices, and then it will be this one. And as you see, now we have a very good probability of Armageddon. And it's like the market pricing it over 3 sets of scenarios, kind of a middle one, a little bit of a good one, and a really, 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 really bad one. But you can say that's overfitting, so we can go and maybe smooth that distribution, etc. But the nice feature is we can choose what is the best way to match distribution. We have a nice trade-off between matching the prices right and getting everything done properly. So that's the key idea. I'll skip this very quickly. If you want to go and price a bespoke, remember, now once we bring a bespoke, all we need to bring is this function for the bespoke, for their own probabilities of default, for their own prepayments, for their own LGDs, and everything else follows because those premiums apply to everyone in the market. So there's a nice feature to it. It's not ad hoc the way we do it. Of course, we need to bring in now very specific information of that portfolio. Let me go to example number 2, which is a CLO, and maybe I'll stop there. So this is a CLO with 270 loans in 5 tranches. And here's what we're going to do. We're going to calibrate them as follows. As we go and look at at loan prices, but most of these loans really don't trade very actively. So instead of doing that, what we'll do is we'll grab the high yield index, and what I'm showing you is the cumulative probabilities of default extracted from spread prices for the high yield index grouped by rating. So let me assume that rating is a decent indicator of credit quality. So the line on the top is for the triple C minus, the lines on the bottom is like a triple B, and these are the cumulative probabilities. And I do that, and these are the average for each of those categories for the high yield index. I also look now, I need prepayment rate, because all of these loans can prepay, or they're cancelable, whichever you look at it. So these are high yield loans, so normally these loans will tend to prepay as the credit worthiness of the borrower increases, and probably increase to the point where it becomes investment grade, and they can actually go and borrow in the unsecuritized market. And they'll restructure it, and they'll cancel the loan, and they will do it. Having said so, you can use this as, you can see this problem as a credit migration problem in 3 stages. You either stay where you are with the loan, you will prepay because you migrated up enough, or you default. And we can look at that, so we can extend these generalized linear mixed models to have multi-state. And we can use real probabilities of default for these things, or in this case, we actually feed them to observe and known probabilities of prepayment in the term structure. So there's various studies from Reuters, etc., that actually have published some of those. And we're going to use, for this example, real probabilities of prepayment. So now we have that. Then we go and calibrate the high yield index. And we find that this is the distribution roughly that we get for the high yield index when we prepay it. Again, very interesting. It's like a 2 big scenario approach, an Armageddon approach. Before I used to have my bad scenarios here. Now my bad scenarios are here, just to keep you on your feet, as opposed to the fact that I'm inconsistent. So that's the key idea. So this is now the risk neutral distribution of the factor, and I'll use a single factor again just for illustration purposes to try to do that. Now we put everything together. One very important point. These are unconditional default probabilities for bonds, which are not prepayable. You need to move to transfer those to instruments that are prepayable. And there's a little bit of a detail there, but when you say 90% of loans of bonds prepay, you really assume that there's a process of something that's there all the time and has no chance of being retired before. When you bring in loans where people migrate up and they can't default afterwards, you need to adjust those probabilities. It's not very complicated, but it's an important point that you need to deal with. So once we have that, we can put everything together. Again, we create scenarios on the systematic factor for a set of them. Hopefully you can see that the green line gives you the... Now we do this for every loan separately and for everything. So this is the average 5-year probability of default, conditional on all of these scenarios. So again, on bad scenarios of the world, then there's very high probabilities of default. On good scenarios of the world, there's very low average probabilities of default. However, we have a different one for each of the underlying loans. On good scenarios of the world, a lot of people prepay, etc., and we put it and we price it. Then under each state of the world, we now calculate the cash flow waterfall for each of those loans. And now you see them with a little bit of noise, because now we have to go and simulate whether loans default or don't default, because there's no partial loss of prepayment. But this is essentially what you get. If you put in more scenarios in there, you'll get it a little bit smoother. There's a little bit of numerical error. And when you price it, this is pricing it actually about a year ago, you get that the A1 tranche is about $100, the D tranche goes to $72. Actually, we priced it in March 2008, so these are the new conditional probabilities of default. A1 went from $100 to $73, D went from $72 to $27. Key point, even if this is based on exactly the same way as all of these things move. I was telling you this figure, we had a bit of a hard time calibrating also the high yield distribution. We got even a bigger bump in there, but this is kind of the stuff we get. There's a couple of other examples. They're described in the paper. These are multi-factor models. So when you have the case of a bespoke portfolio that is a lot more concentrated than the index. So how do we deal? For that, you need multi-factors. You can still calibrate the model to multi-factors. And I have another example there, which is also in the paper, that describes what to do when you have two indices. So say you have a, in this particular case, there's a bespoke portfolio, which is a super senior tranche with 100 names, 51 in North America, out of which 23 are bespoke names, 49 are in Europe, out of which 21 are bespoke. So you need to price this with two indices and with two tranches. And what you find normally is that the implied correlation has to be a lot lower, and you need at least a two-factor model to do it. But you can imply all of these parameters properly and try to price in a consistent way. That'll give you no arbitrage pricing. I'll stop here. There's a lot more detail. We'll be very happy to answer questions if we have more after that. Just a bit of a summary. This methodology will give you arbitrage-free prices. The methodology is very flexible for calibration, sometimes too flexible. So you have to be very careful on how you apply it, and really the devil becomes in the details. It's fairly transparent and easy because the prices can be explained very nicely by looking what the price means in terms of the actual cash flows and in terms of the actual losses, that expected losses that you can see for all of these instruments. And I'll stop here. Thank you very much for your attention.
So we're going now to take questions. Igor? Maybe I'll start with the first one. So we've had presentations of two competing frameworks for dynamic models. And as we said earlier, we don't have much experience in implementing these models into the project. You're biased. But it'd be good to have at least some idea of the pros and the cons.
In pros,
Both approaches, the top-down and the bottom.
top-down versus bottom-up. Well, obviously, as you said, I'm biased. So I generally favor top-down approach, yes. But only to the extent that it can be really generalized to cover single lane dynamics as well. So this is still unknown at this stage. We do have some success. We do manage to calibrate it to single lanes. What we don't know yet how well, how reasonable will be single lane hedges against that. We do have some promising results which will appear soon in the paper that we're working on about the dynamic extensions of this. And it's potentially much, I mean, I wouldn't say much more powerful, but potentially it's quite powerful in the sense that you can calibrate it to so many market observables. It's not just tranche prices, but also bottom-up. I'm not aware of any attempt for calibrating, let's say, bottom-up models to spread correlations or things like that. While you can think of some exotic, probably you can think of some exotic, but for the derivatives that would require calibrating to such sort of information, not just like, you know, I've never seen any example of what sort of correlation between spreads you get when you calibrate a model of type of, like, you know, this Taffy-Gargano, when you calibrate it to tranches and you use all available three parameters that you have, what do you actually get for spread correlations? Are they close to the market or far off?
So first of all, I think we're in early stages. So here's what I think we can do today. I think we can calibrate and run probably by now fairly well dynamic loss models purely top, and we're starting to calibrate, and we can get probably a lot more. If people are trading index tranches and an option on these tranches, etc., the hedge ratios that go between them, the dynamics are a lot better. I mean, from my perspective, someone who doesn't use those, given that we now understand them a bit better, would be a bit foolish to do it. I think that part we understand. We also, I think, are able pretty well to calibrate statically and very well use a lot of information for bespoke portfolios and for cash CDO type of deals, etc. And that, I think we have the tools, it's doable, we have the computing power to do it today. Where we can do today, and I definitely can, but I don't know anyone who can fully do that, is get to the point where we would want to be, which is have a fully dynamic model that can pretty much iterate between bottom up and top down, and you can go and move, gives you the single name dynamic so that you can change any name, put any name back, create any other name portfolios, and get the correlation structure in there. That would be great. In our simple framework, when we try to add dynamics to it, we just get into a dimensionality problem. And everyone that has tried to go full bottom up to dynamic models goes into a big dimensionality problem. And I think the only reasonable approach probably to go to full dynamics is probably to start somehow on the top down and figure out how to then extract that information to the bottom up. Even today, we do that in practice when we calibrate these models. We sometimes will get the first set of distribution from the top down, much simpler model, and then we'll add the more complicated stuff because it becomes more practical. So my view is I think in the end we'll have a toolkit of these things. Depending on what we want to do and how much time we have and what we want to do with them, we'll sometimes apply some of these models, sometimes we'll apply some of the other models, and we'll have there. I do think that in a few years we'll be sitting here and we'll be running some dynamic models that actually do this a lot better. I'm convinced that will happen. We're just not there. I don't know if you think that's impossible.
Well, I think we should view things in perspective, and I remember that in 2005 no one was able to calibrate two tranche quotes, right? And now we have no problem with that at all.
Speak loud. Given the size of the disasters in structured finance, I think that a necessary condition for this type of product to become traded in the future is that firms have the ability to measure and anticipate risk. So this will primarily be asked for Dan, but Igor, if you can answer it, it'd be great too. Dan, with your type of model, have you attempted to do the following? If you went back 18 months and you looked at the Case-Shiller index, if you had done a what-if analysis, if you had said, look at some of the, let's say, super senior tranches that were then rated AAA and valued at par, if housing prices started to fall, would your bottom-up analysis have been able to anticipate not necessarily exactly how much value these would have fallen, but that they were very sensitive to the state of the housing market and that they in fact would have fallen quite a bit in value? Have you attempted to, if you could step back in time, measure that type of sensitivity?
Yes, you can, but it sounds great to say it after the fact, but let me cover two points, because I think your point is very important. One of the things we didn't do over the last few years, and that's why I think that this is one of the issues that happen in crisis, is we were very comfortable with top-down models all the way to where ABS CDOs, we model the underlyings as bonds, and then we put in a corporate correlation to put them there, even though those correlations, if we had modeled them so simplistically, those should have been. The lack of ability to go down to the underlying and to the single names and to the underlying collateral in the case of housing, I think is one of the biggest mistakes we made as an industry, to ignore that bottom up. And actually, it doesn't have to be bottom up to ignore that bottom, to stay at the top and not go down back. And to the degree that we can go, I don't think we'll do that again. I'm hoping we don't. I hope we've learned the lesson. And we've shown examples a lot where if you're not careful, and it becomes very important, you can go and look at CDOs that look great, but once you start looking at them, the average is a lot worse than the average from the prices. And then there's some CDOs or some IBSs that are priced very low, but yet the collateral is actually pretty good. And I think that a lot of people are starting to make money going and checking that. With respect to the systematic factor, I think that systematic risk is very important. I strongly believe that we need models that use systematic risk embedded in it. And I think if we had calibrated the prices in the models at that point, as the curve was going up, we would have got perhaps some bad betas or correlations, but we would have got correlations that would have told us what would happen if they go down. Would have they been the same? I haven't done any numbers on it, and my guess is probably not, but we would have gone and seen that could not have continued. That's number one. And number two is people needed to go to look at the collateral in detail and say, there's subprime, 2006, that is going to reset in 2008. The data that we have for all of before doesn't really hold for what we have now. So for that, I don't know what to do. I mean, now we know what to do a little bit more. I mean, it's like, I'm sure you guys have heard the joke, but it's the quant that goes to his boss and says, I have really bad news, some good news, and awesome news. He said, what's wrong? He said, the really bad news is the estimates are that about 8% of all homeowners are now defaulting, and we're going to have to get their houses back. So like, oh my God, that's awful. So what can be good news? He said, well, we have where to park the cars of all the car loans. We have. That's when he said, what are the great news? He said, I'm a quant. I have data. I'm having a hard time calibrating the model, but I came up with a new model, and I think we're going to model things better in the future. So for us quants, it's a good experiment and a good time in the sense that we got some information and we have a good opportunity to get our models better, and hopefully we'll get it right or better next time. But I think your point is great. I think it's very important to not ignore that systematic reasoning. We ignore it. People talk a lot about contagion, and there's contagion, and I think that's important, but what might be contagion for some is systematic for others. I think the problem is systematic reason, not contagion, in my personal opinion. But
it's more like the same.
Yeah, it's just what you use as underlying factors, right, for driving it.
Yeah, yes? Speak loud.
Basically, I have I believe it's a more fundamental question. Perhaps it's my lack of understanding of how both the top-down and bottom-up approaches are functioning here. But I see in both cases, you tend to start with either an individual solution, which has a specific type of distribution category, or you're starting with a collection of items that have specific characteristics of distribution types. And as you move forward to try to find out that next piece of information, what's happening is calibration here. My question is, in the first place, do we even know that this process is closed under the operation that we're looking at? If we start with some particular collection of distributions, can we know a priori what kind of distribution we're going to see at the end? Never mind what it's going to tell us, but even the simple aspect of, is it closed under that operation to even retain the type of distribution we use?
To be honest, I'm not sure I understand. So the question is, we're making some. Let me try to restate it and see if I understand it. So in any of the two models, we need to start with some assumption that either in the top form of what are the possible set of events, and let me try to rephrase it a little bit, that can be caused by that characterization of the model as a whole or as individual things and how they aggregate together. Do we understand? Do we know? I'm not exactly sure what you mean by closed, but I think if I understand correctly, I think you mean, do we understand what set of possible values for distribution we have as we match for the future?
If you started with a Gaussian distribution, are you going to end up with one? If you started with an airline, will it look like an airline? I mean, do we even know that much?
I think we do, actually. I mean, so let me. In the simplest cases, we do, and this is a typical. But by the way, in the non-parametric calibrations that I show you, the answer is no, we don't. That's the whole point. And sometimes we get these multifaceted ones. My understanding of the birth and death processes stuff is we have a pretty good understanding of the type of distributions we can get, right, as we move along.
Well,
in terms of the laws.
Yeah, in a top-down approach, the statement is that the general form, which was the semi-parametric form for the portfolio intensity within this nonlinear death process, is the most general parameterization which is consistent with no arbitrage. So as long as your tranche quotes are free of arbitrage, then you can always fit them into this sort of parameterization. But because it's non-parametric, there is no such question whether we stay in the same class or not. We will stay in the class of non-parametric distributions, which is parameterized by these contagion factors that I introduced there. So it is closed set.
Yeah.
What I always worry about in models like this is what I call stability. Do you have any at all reason to believe that that changing the set of inputs within their measurement error will not move you outside of reasonable bounds on the outputs? I don't see that these models can even address that. It's too many input parameters, and the path from the input parameters to the output is so complicated that I don't see how you address limiting the fluctuation in the output just by changing in some arbitrary way the inputs within their measurement error.
So the question is about stability, and that, yes, it's a valid point. It's a good one. Indeed, all what is common between the models or the class of models that Dan presented and I presented is the fact that both are non-parametric models, and as long as you deal with model that has a flexible, variable number of parameters, then you might tend to overfit. And as long as that's the case, then you can run into these issues of stability and you can get unstable deltas, etc., etc. But there is actually a very simple way to ensure stability. So there is a balance between in non-parametric formulation, you can achieve a balance between goodness of fit and out of sample properties by adding something to your objective function. So basically, you can smooth out your implied distributions for the factors, like those that Dan showed, such that they will become less erratic, but at the expense of having a little bit worse fit to prices. But what you gain instead will be more stability. So technically, it's not difficult at all. Maybe
I'll add something. I think your point is very good, and I'll take a purely engineering view on this one, which is I think you can actually you need to ask what are you going to do with these models. And one of the things we do quite a bit is try to address model risk, because first of all, I think the problem goes beyond that in this type of instrument, because many of these quotes and prices are not exactly real quotes and prices. This is not necessarily what you will go and price for. So we already start, I'll start a step earlier, which is we might not even know that we're calibrating to the real thing because we don't necessarily observe that real thing. So we have to be very pragmatic about it, and I think model risk will and should become a much more needed subject to address in the case of all these illiquid instruments. I know there's another AFE session where Charles Smithson is going to talk next week, and I know he's probably much better than I to address this point. But this is a very important point. What does it even mean to have a price for all of these illiquid instruments? So I worry less about the numerical stability. I think we know that the mathematical tools and computational tools. And I worry a lot more about the quality of the inputs and what we want to do with it. And I think the answer depends on what you want to do with it. If you want to hedge, you need certain things. If you want to use this for mark-to-market, you need certain things. If you want to use it for risk, you need certain things. And I wish there's a simple answer to your problem and the reason. But I think we have the engineering tools to make those calibrations more stable if we need to. That I feel fairly comfortable we can do. I don't know how to address in an easy way the fact that these prices are, I'm not sure that they are prices in the end. And that's a real problem.
Just the last question, because we are over time.
Do you envision the standardization for this model? I mean, how do you convince more and more participants to use this model? How effort do you think you would have to put in there? Do you think Gaussian coupler will replace this kind of thing?
I hope so. I'll be very honest. I think when we came out with that model, and it was a great advance, it helped us do some stuff. It's a really good quotation thing, but it's not Black-Scholes. Black-Scholes is a consistent model. Its hedge parameters make sense. It comes from some dynamics, etc. The Gaussian coupler doesn't. It has a lot of limitation, a lot of ad hoc. Having said that, it's a very nice communication tool. People feel very comfortable to talk about correlation prices. I would like to keep the good parts and get off the wrong parts. I think talking about correlation is a nice thing, so maybe we can keep on talking about correlation, but you can get those correlations from a better model. And personally, if I had to put a bet, I think we're going to use dynamic models, and I think we're going to use this type of factor models. I don't see why. We've been using factor models for portfolio credit risk now for the last 15 years, and to me the fact that we're not using some of that information when we price portfolio products, I think we will have to. I think it makes sense, and I think there's a challenge to convince a lot of people who have been used to doing it.
I think we keep using the Gaussian coupler model to price, to quote prices, and hedge our books using a dynamic model. I suggest that we stop here and we keep, discussing at the bar.
Thank you very much.